Hello and welcome back to Calculus 3. We have triple integrals for today, and we are going to cover rectangular and iterated triple integrals, and then the next lecture would be different coordinate systems for triple integrals, namely cylindrical and spherical. But now we're going to do the basic stuff with dx, dy, dz. So first, I'm going to just make sure we all understand the 3D we have x dimension, y dimension, and z dimension. Those would be the 3 dimensions. And now we introduce the representative ice cube, or whatever you want to call it, which is going to be dx, dy, dz. All of these are infinitely small, and you can think about infinitely small as a grain of sand, speck of dust, and then it goes down to an atom, whatever, right? Infinitely small. And when you put them all together, they fill the entire space of the container, giving the volume for that container. So I can express my volume integral as the triple integral dv, right? Triple integral over some region d. And that would be 3D because dv is the volume, where dv is dx, dy, dz, or one of those combinations, right? You have 6 different possibilities there. So if you want to calculate the volume, you can just use the triple integral. Yes, you can do the double integral as well, right, with the function inside. Or you can do the triple integral without the function inside. But then if you move to the 4D realm, right, bulk, would be triple integral over region D of a function x, y, z times dv. Again, dv is one of these. So we can use triple integrals to compute either volume, if we don't have the function inside, or to compute the fourth-dimensional value with the function inside. What is this function? Temperature function, density function, whatever we want to calculate. So 3D case and 4D case. Now, as the double integrals, we are going to have the easiest basic form that covers the box, right? You have a regular box, like you look at your desks, for instance. We are sitting in a classroom that is octagon, so I can't really use this classroom as a model, but usually classrooms are boxes with 6, right, sides. So we can think of the rectangular integrals where in the 3D realm over here we have our x, we have our y, we have our z. So let's say this goes in x 2 units, it goes in y, let's say 8 units, and it goes up in z 3 units, whatever. We know that the volume of that would be 2 times 8 times 3 for the total of 48 units cubed. Now, is there a way for us to deal with this as the, if someone says, but why, right? And you say, well, yeah, volume is going to be the triple integral dv. You decide over region D, right? And then you decide that the triple integral, you're going to use, let's say, dz, dy, dx. What are the limits of z? Well, it's a rectangle. So it's 0 to 3 on the inner one, because that belongs to z. Middle one is the y, so that's 0 to 8. And outer is x 0 to 2. So when you compute this, you have two outer integrals, 0, 0, 2, and 8. The inner integral is just z computed from 0 to 3. You still have dy dx. So now that's the double integral 0 to 2, 0 to 8. This becomes 3 dy dx. Then the inner one is going to be 3y from 0 to 8. Still have dx, 0 to 2. So that's going to be integral 24 dx. And then you have your 24 computed from 0 to 2 to get your 48, which was. So this is the way to deal with this. So if you have a rectangular integral in triple integration, we can write it as, so this is the rectangular one. Rectangular triple integral. Would simply be triple integral fxyz dv over region D would be a, b, c, d, e, f, fxy, z, and now I'll put the z, dy, dx, but the order can be changed. So this would be our integral, rectangular integral, and this only works for the boxes. Like nothing, that's it, just boxes. It's a very limited use, which is why we don't use it, right? And you actually can, right? You can just use this. So why would you even integrate? Yes. Where? Oh, over here. Yes. 24x. Very good. Very good. 24x calculated from 0 to yes. Thank you. So very limited use for this integral, but it actually helps us understand that, you know, we have a base to start, and then we are going to swap these integrals and put the functions in their limits, and then we can create shapes in space, right? So that's the next step. So now, to improve this to, you know, general triple integrals over general regions, right? So general case. General case, we are going to take a look at the triple integral on the region D of fxyz dv as the triple integral. Now you'll need some space over here to space them out because we have to write stuff there. And we're going to use fxyz. The z dy dx is the standard one. Now obviously sometimes you will have to change the order, and then you just have to be careful with your limits. So it would be beneficial if you just stare at this as I am deriving it, so you can actually swap the order when you need to. Outer integral, right? You remember that I always say whatever is the outer one, dx, dy, dz, whatever is on the outside, that's the main one, right? So that one gets the numbers on the outer integral. All right? Then this one and this one belong to y, so they have to be y equals, and it needs to be a function of the only one that it's not integrated yet, which is the one at the end. So those have to be, in this case, in this string, that has to be function of x. So I have g of x and h of x on the inside, because those are the ones that the only variable that is still allowed to be there for the last round of integration. And then now this one has to be g of xy and h of xy, because you're integrating z. So these limits, this limit over here is x equals, this limit over here is y equals, and this limit over here is z equals. So that's how you know it's completely reversed order from what you have on the other side. So z is a function of x and y, g is a function of x only, and a is just numbers, right? The x is just numbers. So this is the standard one for us. And I need you to practice this right away. So I'll put this in a... I'll put the barbed wire around it too. There we go. So that's the main one. Now I would ask you to write a formula for dy, dx, dz. I want you to write this over here for dy, dx, dz order. So you just write triple integral, put the limits. You know this is going to be x, y, z, and I gave you dy, dx, dz. Just fit those. I want you to fit the limits. All right, well, that will be enough time. Outer is z. If outer is z, then I have my EF limits, right? Because A, B, C, D, E, F. EF is for z. So EF goes on the outside. The inner integrals are x as a function of z, because middle integral belongs to x as a variable, and the last one that is to be integrated is z, so we have to have this. So we'll put g of z and h of z, and then the last one is capital G of z and x and z, and capital H of x and z. And there you have it. That will be the setup for, because not every object will be set up using the z, dy, dx. We have, and then you can, practice. Just writing the limits. Practice for dy, dx, dz, and dx, dy, dz. You have these, so you can practice for these and get them. Settled. So we have our problem, and now I would like to use this idea of setting things up to set up problem. Let's deal with the wedge. Yes.
Wait, shouldn't it be d of c instead of f of e instead? For the first interval, but shouldn't it be d and c instead of f and e?
It's z, right? And z integral over here, z, ef.
Okay.
Right? The c and d belong to y, because those are the second two. Usually, that's what we do, right? X, a, b. Right? X belongs to a, b. I mean, a and b belongs to x, c and d belongs to y, ef belongs to z.
So we're always giving the outer.
The outer limits are always numbers, so that you can come up with a finite number. You can never have variables in the limits on the outer, because that would end up with an integral that would have variables in the answer. But you need the volume, right? You need a concrete value at the end. So the outer integral always has to be numbers at the end, so that you can compute the value. So let's take a look at this problem with a wedge. This is set up a little bit differently than you used to. So I have the wedge going that way, going this way, going up, and straight, going that way, and this way, and there. So it's a wedge. We have our x, y, and z. Numbers are 2, 4, and 6. And we would like to set this up. What is the volume? And these numbers are everything that is given to you. You see that this particular wedge is bounded by 5 planes. Do we all see that? 5 planes. There is an easy hack way to do this, right? If you imagine that this was actually a box, like that, well, you just need to cut that box in half. So it's very easy to go, oh yeah, it's just 6 times 2 times 4, 48 divided by 2, the answer must be 24, right? So you know what the answer is. You know the answer is 24. But is there a way for us to use the functions and things that we just learned about to get that 24? And the answer is obviously yes. But now you need to figure out, the order dz, dy, dx, dx, dy, dz, dy, dz, dx, right? Which one of those 6 do you want? And multiple would work in this case, but you know. So what I like to think is, let me do this like a double integral kind of deal, where the third integral, the one on the inside, will be actually top minus the bottom functions, right? So what do I have? I have the plane on the bottom, z equals 0. I have plane on the top, z equals 6, because it's flat, right? It's horizontal plane, and the horizontal plane is going to have z equals 6, because it's on elevation 6. I have this back on this side, and that's y equals 0, because it's the xz plane. Then I have the one in the back, and that one is yz plane, so that's x equals 0. That's good. And finally, I have the front over here. And the front is going to be a plane. And you see that that plane is parallel to z-axis. And if it's parallel to z-axis, then it means that it's sufficient to figure out what's the equation of this line. It will have the same equation as that line, because it's parallel to z-axis. So what do? You draw the xy domain. Your y goes up to 4. 1, 2, 3, 4. And your x goes up to 2. So this is the bottom. There we go. So that's the bottom of the thing. And if you take a look at this line, this is y equal mx plus b, right? The slope is rise up over 2, right? Rise up and over 2. So that's rise negative, and it's negative, right? Because rise is 4, it's falling down. X plus 4, y-intercept is 4. It's a linear line. So this is y equals 4 minus 2x. Great. Y equals 4 minus 2x. So now we have all of the planes that are in... Mechanical engineers, pay attention, okay? Because this is your life. So now we have the entire shape bounded. And again, this is the cheapest possible case because they're all planes. So now I need to decide which model I want. I'm going to go with dz, dy, dx. Because, sorry, dx, dy, dz. Because look at my z's. No, dz, dy, dx. Look at the formula here. It's in terms of x, right? So y is in terms of x. That's going to go in the middle integral. And then in terms of x means x should be calculated last. Just from looking at one of these planes, I go, okay, if I have y as a function of a single variable, that means that that's the only variable to be calculated in the future, and then leaves me that the y should be the middle integral, and then this would be the last integral by process of elimination z is first. You will really have to go back and, listen to it again and figure out a few times. I'll say it one more time. So looking at this equation here, I see that y is the function of a single variable, and that variable is x. So in my limits over here, and if I look at both of these integrals, the middle integral is always the one that it's in terms of a single variable. And that single variable is the one that will be calculated last, so it's the 1 in the end. Okay, so now that I picked the order, I put the triple integral here. I don't have a function because I'm calculating volume, right? So no function. And I know I'm doing dz, dy, dx. Great. So what are my z's? Well, 0 to 6, because it's a flat plane, right? What are the limits for my y? Well, y is going to go, the back is, you have the y equals 0, right? The vertical one goes all the way to this one. So that's 0 to 4 minus 2x. And x goes from 0 to 2. Now, if I am to draw, look at this. I'm going to draw with the red representative rectangle on the bottom, which would be representative rectangle like this on the triangle. So ignoring z, because z is very easy, right? Flat on the bottom, flat on the top, 0 to 6. Ignore z. We're technically setting up a double integral, and then we're just going to put another one for z's. So look what we have in a domain, right? You have the representative rectangle swiping from left to right from 0 to 2. Your limits on x are 0 to 2. And the height of the integral is stuck between 0, which is y equals 0 on the bottom, and the top is writing 4 minus 2x. Bueno? So we're technically focusing only on the double integral, and then we just squeeze the z in with a 6. Now, anytime when you have this single integral like this, 0 to a number, this situation here, that's just immediately going to be equal to 6, right? Because the integral of dz is z, and then you plug in 6 minus 0. So you might as well memorize immediately, like anytime you see this situation, it's immediately whatever the limit is. You have seen this already here, and you've seen it 3 times, actually, right? So here it is, and it works out to be 3. Boom. And if you ignore the 3, that would be 8. 8 times 3 is 24. If you ignore 24, this is 2 times 24, 48. So, you know, you might want to speed up a little bit your calculations as you go to solve this. We're looking for 24, if I remember correctly. So I have my double integral, and now this is 6 dy dx. I gotta buy a new tip for this pen because it's getting very difficult to write and keep skipping. Integrate the inside, you get 6y. Calculated from 0 to 4 minus 2x dx, which is going to be integral 0 to 2, 6 times 4 minus 2x, don't worry about the 0. You could kick 6 in front of the integral, you can distribute. Personally, I would pull 12 out, and that leaves you with 2 minus x to integrate, which makes everything easier to compute. Right? Do we all see the factor 2 in parentheses? 2 times 6 is 12. Kick that in front of the integral. So this is going to be 12. And now you have 2x minus x squared over 2, computed from 0 to 2. 12 times 4 minus 2, 24 as promised. So the whole problem is quickly 24. We all good? Next problem. I have some wonderful examples. Whew. Beautiful.
Boom.
How about that? It's amazing, right? I need you to focus on the method that we are going to use. You see me draw on the side XY plane where I had the triangle with the representative rectangle dx. Note that your domain plane is going to be xz now. And that gives you xz, which means that the y integral must be the most inner one. That's another thing. So sometimes you look at the shape and you immediately come up with the order of integration, right? The way the shape is positioned, the way the functions are given to you. So as you are looking at this shape, right, you can think of football if you want. It's something close to it. This is actually, as you can see, the domain is elliptical, right? The football is round, so football has a circle. This one is an ellipse. So what do? You shine the light along the y-axis, and it gives you the shadow r. And shadow r is your domain to give rise to this object. And whatever your domain is, those are the two outer integrals, and then the third one is your most inner, sorry, the other way around. The function, right, is the most inner integral, and the domain ones are the two outer, right, the middle one and the outer one would be the domain. So to draw this, yep. To draw this, it's better for you to look at the original object than what I'm doing. Functions are given to us. Y equals x squared plus z squared. And y is equal to 16 minus 3x squared minus z squared. And that's enough. That's all we need to know. You have two shapes that are intersected. Please. Good. You have two shapes that are intersected. And as I said, you put a flashlight over here. There's a switch over there. There we go. You shine the light. What it does is it creates a shadow R, region R, shadow, which creates your domain. Now, I draw that domain. It's an ellipse in, oh, come on, pen, stop doing that. XZ plane. And the way to get this line, set two functions equal. because you are eliminating one of the variables. Which variable you are eliminating? You're eliminating y, because the one function over there is y equals, the other function is y equals, and then when you set y equals to y, you eliminate y completely, which means whatever you got is sitting on the xz plane. So we set these y's together. You get x squared plus z squared is equal to 16 minus 3x squared minus z squared. And now you just solve this. You move 3x to the other side. You will get 4x squared. Move z to get plus 2z squared equal to 16. And if you remember anything about your equation of the ellipse, right, you will divide everywhere by 16 to get x squared over 4 plus z squared over 8 equals to 1. This means that on the x-axis, the numbers are 2 and negative 2, and the top and bottom, negative square root of 8 and positive square root of 8 for these. Green? All right. So now we have this, and I know that I will have to write my, well, let me do that red. I used to do it red. I will have to write my representative rectangle dx this way. And you see that now, since I'm drawing dx, that's my outer. And then the other variable in this domain thing is z, so that's the middle, leaving the y to be the most inner one. So the order is dy, dz, dx. Again, I drew dx because dx is going to swipe from negative 2 to positive 2, giving us the numbers on the outer integral from negative 2 to positive 2. So we have that. And then the height of this is the lower portion and the upper portion of the ellipse, right? So we have those. And then the only one variable that is not used is dy, leaving that to be the inner one. But we already have limits for y. Don't you all agree? We already have limits for y given by basic functions. It's the one further away from the domain. On the top limit minus, lower limit would be x squared plus z squared, right? One the closer to the domain shadow. It always goes, whatever the shadow is, right? The one that is further away is the top limit. The one that is closer by is the lower limit. We are still setting ourselves up to set up the integral. Then we have to solve it later. So procedure from scratch one more time. I have this object laying on a side with the functions given to me as y equals y equals. I shine the light on the y-axis, which gives me a shadow of the object here, which is what I draw as my domain. To find a line for that domain, I set the two functions equal to kill off the variable that it's not in that plane. Right? So y is eliminated, and we got the equation of an ellipse. Draw that ellipse. Maybe you draw the circle at the first time. I don't know. But now you see that this is not a circle. You know it's ellipse, right? Because radii are different. You draw the ellipse. X variable will have square root of 4, which is 2 and negative 2. And z will have radius of root 8, because square root of 8 is root 8, right? That's 2 root 2. So negative and positive. You draw dx, and as soon as you draw dx, you know that dx is the main one, all the way at the end of the integral, immediately meaning negative 2 and 2 are its limits. The other variable that is involved in the domain, in this case z, is the middle one. By process of elimination, y is left to be the inner integral for this problem. So now that we have all of this, we go and we write all of this in the triple integral, and then good luck with the rest, right? So what do I have? We don't have a function, so we are still calculating the volume. We know that our string is dy, dz, dx. We see that our dx is -2 to 2. That's good. The other easy limits are y's all the way on the inside, which is what I said. The one that is closer to the shadow goes on the bottom, so that's x squared plus z squared. And the one that is further away from the shadow, 16 minus 3x squared minus z squared, is the top. The only one that has stayed is the inner integral, and that would be the top and the bottom equations of the ellipse, because you cut the ellipse in half on the x-axis, the bottom one. So you need to solve, I'll do that in blue, you need to solve this equation for z. So you have z squared over, well, actually it's easier if you solve from here for z squared, right? So you have 2z squared is equal to 16 minus 4x squared. Z squared is equal to 8 minus 2x squared. And then z equals plus minus square root of 8 minus 2x squared. So these are your limits. You have the lower one to be negative square root of 8 minus 2x squared, and the top one is positive square root of 8 minus 2x squared. Yeah?
Why wouldn't it just be plus or minus root 8 if you made the x values -2 and 2?
Well, you can't do that because the x limits are for x's.
So I'm saying, like, the z ones are negative root 8 to 8, you drew out in the ellipse.
What you want me to put -2 and 2 and negative root 8 to root 8,
Yeah.
right?
Yeah.
That corresponds to a picture like this. It's a rectangle.
To make the y, yeah.
Make sense? Thank you. So when you have just numbers, your domain must be rectangle.
Yeah.
That's it. You don't have rectangle, you have ellipse.
Yeah.
So you have to use the functions. There is the upper function plus the lower limit lower function. And then you have your round ellipse. If you just put numbers, it means it's a rectangle. It's a box. It's a good question. It's a very good question, and it ties in a lot of stuff. So thank you. It's the functions, yes.
Can you go from 0 to root 8 minus 2x squared, which multiply times 2?
In this case,
Only if it's like only if it's symmetric.
if you have radial symmetry, if you have, there's so many things.
Not worth it.
Never. I'm sorry, but that is a very smart thing to think and do. But the dangers of doing that for the double and triple integration, because you have a perfectly symmetric domain for double integrals. Let's go back, double integrals. And you have a perfectly symmetric, you can call it rectangle, you can call it a square. Take a square. And the top is slanted. If you cut in half, look at this, right? You have, so your slant is like this. And you have a perfect square in it, right? And you cut in half to double because you didn't want to go from -2 to 2, you want to go from 2 to 0, because it's easy to compute at 0. Do you see how when you cut in half and you compute 2 to 0 on this side and double by 2, you overshoot a lot? Because the slant makes it that there is much less volume on this side than on this side. But by doubling it, I don't want to break this in half, but you have like the top of M, actually, if you double it. But you don't have a top of M. So doing those tricks from Calc 1 with doubling the integrals in any kind of 3D environment is very tricky and very dangerous. Can it be done? Sure. Can it be done in this example? Yes, right? But just, you know,
Yeah, I got you.
do we play with fire all the time? Yes, we're careful, right? We do play with fire all the time. So that falls under that category. Guys, the rest of this is, you know, just good luck. Yeah. All you need to do is to integrate this, and you're done. Now, you know, if you are really comfortable with these calculations like I am, you know, you immediately know just by looking at this that the answer is 32 pi root 2. It's just, you know, it's obvious. But everyone is looking at it like, what? It's obvious. I mean, come on, look at it. 32 pi root 2. See? Obviously. It's easy. All right. Well, it was worth at least for 5 seconds. Oh. Yes.
So this is kind of like how we go about doing the egg thing.
Except you don't get these. You have to figure them out.
Yeah.
So that's the part where you enjoy. The rest is technically what you see.
So I guess I'm kind of confused. So this is for 4 dimensions, right?
No, this is we're looking for volume because there is no function right here.
Okay. So
If I plug in a function, so
40.
yeah, so you can use double integral for your egg problem, or you can use the triple integral for your egg problem. It doesn't matter.
The difference is
Yeah.
the triple would just have.
Which is now you're giving me an idea for the next time to improve the problem by looking for densities or something.
And so, just out of like curiosity, go into the egg problem. So, like, if we're standing an egg up on its end and it goes like long ways from origin to z, it's like it's not symmetric because like the bottom is like a circle and the top is a
Parabolic, yeah. You have
So,
to.
Do we treat that like a piecewise function?
No, you just treat it as top and bottom.
Okay.
Top minus bottom, right?
Okay.
In the integral for double, or lower limit, upper limit for the integral that it's. Yeah. So yeah, it's a lot of fun. Good. Who wants to integrate this, real quick? Hamid. Okay. Fine. It's like, yeah, who wants to integrate this? You. Sure, why not? Right? That's it. Cool. There we go. All right. So what do we have? We have the outer, well, and then the square root over here and the square root over there. I said that the inner one, right, would just be the 16 minus 3x squared minus z squared minus x squared minus z squared, right? That's the top limit minus the lower limit, and we still have the z and the x to worry about. So this is now double integral, -2, negative root, +2, positive root. We'll go back and pick up 8 minus 2x squared. What do I have here? I have 16 minus 4x squared minus 2z squared dz dx. This looks awful, right? But guys, you have squares over here and you have square roots. That stuff is gonna cancel. Don't panic prematurely, please. Right? It's gonna be great. Maybe. I don't know. We'll see. What am I integrating? I'm integrating z. 2, oops, -2, and then 2. And what do I have? I integrate z, so that's a 16z minus 4x squared z minus 2z cubed over 3, computed from negative square root of 8 minus 2x squared to positive square root of 8 minus 2x squared. I still have dx to worry about at the end. All right, so what's next? Next is the integral -2 to 2, and now we have to plug all of this in. So this is going to be 16 square root minus 4x squared square root minus 2/3 square root cubed minus and minus will give me plus 16 square root minus from the formula, minus from here, minus from there is a minus 4x squared square root, and then minus from the formula. So all of these are doubled. Dx is just a lot of writing. So I have 32 square roots minus 4x squared square root minus 4/3 square root cubed, all of that dx. And now we have negative 2 to 2. Oh, by the way, these are the wrong coordinates to do this in. You can tell that, right?
Yeah.
Because it's circular. So what are we looking for? We are looking for polar, which would be upgraded in our case to the cylindrical coordinates. So this would be literally 2 lines calculation in cylindrical coordinates. But that's next class on Friday. So redoing this problem. Actually, you know what? Stop wasting time. We should. So here it is. 3 dots equals to 32 pi root 2. Use 13.5, right? That's the, yes, 13.5. Perfect. And then we can go and spend time for important stuff, which is setting up the ones that you actually will be computing, because if you see this problem on the exam, and this problem is actually easy for the exam, if you're using 13.5, you will be using 13.5. You won't be wasting your time. Because now I have to do what? I have to do trig. Yeah, I have to do trigs. Even though that cube over there, it doesn't help us, right? Actually. So we have to do trig subs there, and that's why the polar coordinates are there to make everything better.
So we should use 13.5 for the egg problem, not 13.3.
You can use whatever you want. The idea is to set it up in one and then use whatever. Oh, you mean calculation?
Yeah.
You're planning on calculating anything by hand for the project? Why?
Because you said you should look like.
Project is all about you writing things and making it look like $1 million. I'm not going to see a single step of your calculations. So I would highly suggest you don't compute anything by hand for the project. I have your, I'm not going to see any of the steps. What is going on with this thing? I'm not going to see any of the steps. I'm not going to see any of the stuff. So. That's next lecture. Cylindrical integrals. Cylindrical. Triple integrals in cylindrical and spherical coordinates. So that will solve this like nothing. We're not going to have to, yeah. So that's next lecture. Let's go and set up some other cool from the homework. Here is what the homework looks like. We have this wedge on top. You have 4 triangles, which is actually 4 planes that are intersecting such that they form triangles. And again, I have no clue why, but they give you the formula for the plane. You should be able to find the formula for the plane because you have 3 points. That was in your first exam and the second exam, right? You have 3 points, you create 2 vectors, you cross those 2 vectors to get the normal vector, you put the points and subtraction, and you come up with that equation. There is no need for that equation to be given because you know how to find it. You have to get this z equals sine y, because that could be parabola, could be sine, right? It's not clear, so you must have sine y there. You do not have to have x equals y, because look at the points, pi comma pi. That should be clear that x equals y for that side. Over here, I don't know if this is a ball or, you know, ellipsoid, so sure, I need the equation. On the bottom, sure, I need the equation, right? How wide it is and all of that stuff. So these equations I have to have. That's great. So all of these problems, as you can see, they're all calculating volume. No one is talking about computing anything. But to be completely honest, it's not a problem. You have function plugged in here. So this is your 4D problem, where x, y, and z region D is given as, and look, it's a box, 1 by 2 by 3. So these limits are 0 to 1, 0, oh, sorry, negative 1 to 1, 2 to 2. So the box is 2 by 4 by 6, actually. Are you going to exercise symmetry here? No, because of this, right? If there was no function and this is all perfectly symmetric, sure. 0 to 1, 0 to 2, 0 to 2 times 8, right? Because you cut each dimension by 2. See, these are a lot of things that come, right? You can't go and say, oh, by 2. It's by 8, because each dimension you cut by 2. So there are a lot of subtleties if you want to use. Over here, again, the symmetry broken, right? X, y, and then e to the x. So it's very difficult to come up with all of the little tricks. All right, cool. We did the problem with the wedge, 18. You can use that problem to practice at home, and then you have the guide, right, one we did in class. Problem 19, amazing. 19 is amazing. Here is the same problem set differently, 20. This is almost the same as 17. Very close to the egg, actually, right? Skateboard ramp, or whatever that is, that function is e to the y. E to the y is round, right? So, you know, those extreme sports things, when they go, they break their teeth, and then they can't say anything on the interview. So these are the, you know, that could be the design of the ramp. Pipe cut in at these angles. What is the volume? All different kinds of shapes. This looks like a sail over here, right? It's like how much volume of the wind is going to catch. It's like you can come up with all the ridiculous things to just fill in blanks. Why would you compute something? But as I said, I mean, or you can just look at all of this and say, yeah, it's mathematical gymnastics. Let's just do it because it's fun. I don't know. That's that. So let's set up. Let's set up two of these. I would say, you know, setting up these is much more important than actually computing them. That's your life is going to be setting them up and then asking computer to solve it, which is the same thing that I'm requiring you to do on a project. You have to trace that egg on a paper. You have to figure out your equation in either centimeters or inches. You have to have that equation, and then you have to set up the integral. And then my hope is that you're just going to plug all of those terrible decimals and things that you have in Mathematica and just get the number at the end. And, you know, spend 3 paragraphs or so talking about the process with, you know, pictures you took of the process and things like that. That's the idea of the project. I'll see your steps on exams. I'll see your steps on labs where the problems are friendly with numbers that are friendly for you to compute without technology. Let's set up problem 20, and then you can practice 19 on your own and check the work in the back. Problem 20 has this wedge. So you draw looking at that thing over there, and I'll switch once I'm done. So try to draw this as best as you can. Looking at problem 20. So it is this rounded wedge. In the back, we have y equal x squared, so that's the back of this. I know it's way too busy, but back is y equals x squared. And that x squared wraps all around. Top is given by z equals 3 minus y. And the bottom is z equals 0. So there are only 3 surfaces here. Like you can only color 3 different colors. The one that wraps around the object, which is y equal x squared. The slanted top, where the dust would fall, right? If this is some kind of figurine or something to stand on the shelf. The dust would fall over z equal 3 minus y, and then the bottom on which it stands, z equals 0. So only 3 surfaces, and that's why I only have 3 equations. So what am I going to do? Well, shine the light on the top. As I shine the light on the top, it gives me the xy like this. xy. And I draw immediately my delta x, right? dx. And I immediately see that I have a lot of stuff that I need to figure out. What are the endpoints for x? Because it's going to be from that value to the other value. What is the y value on top? Right? So once I know those, I can deal with everything else. So how do I figure out all of these things? Very good. We set 3 minus y equal to 0 because that will give me this line here, and it immediately, because look guys, you have the one on the bottom. I need this 3D printer in the classroom like so much, because just 3D print this and then just show. You have the bottom, which is flat. You have the slanted top. They meet at that line. So when I set z equals 3 minus y, and z equals 0, I will have that line. So what I have now is when I set these two equal, I get 0 equals 3 minus y is equal to 3. Yay! I just found that y is equal to 3 on the top. As soon as I know that y is equal to 3 on the top, and I have that y equals x squared, well, 3 equals x squared, I know that x's are plus minus root 3. So, negative root 3 and positive root 3. I already drew dx, and another variable there is y, so I immediately know my order of integrals. It has to be dz, dy, dx. Can I write z? dx. Because x is I drew dx, representative rectangle, so that means that's the one on the outer. The other one that it's represented in the domain where I shine the light to create the shadow is y, so that's the middle one, and then by process of elimination z is on the outside. Great. So what are my z's? Bottom of the z is 0, top of the z is 3 minus y. What are my y limits? Anyone? I would agree with 3 and I would not agree with 0. X squared to 3, very good. The bottom of the representative rectangle is writing x squared. The top is writing 3. So it's between x squared, right? You see that the red representative rectangle is trapped between the x squared on the bottom and y equal 3 on top. So x squared to 3. I'll do some, and then negative root 3 to 3, that should be clear. Let me draw something here, guys, and then so let me just point this out. This hopefully will help. Look, I'm going to draw this, and I'm going to say, actually, bad. Let me do this, and then the blue one. The blue limit is 0 to x squared. The red limit is x squared to 3. And here's the green one, the whole thing, integral 0 to 3. Do we all get that? So we have to be very careful with setting these things up, because one wrong limit, you immediately have a different shape, and everything is off. Volume is off, and then everything else gets good.
So you count to like the subtraction of top minus bottom.
Always. We are not doing anything different now.
Yeah.
Because your limits are always going to be f of a, f of b minus f of a, right? So it's always top minus bottom. Now you decide to stuff that in the integral for the limits, or you can just do it inside. It doesn't matter.
Now, say we were to switch it, like, depending on which way you look at the shape, when you shine the light over it, can't you do, instead of x squared to 3, can't you do 3 to x squared, depending on which way you look at it, and switch around the...
Well, if you turn the object upside down, but there are different problems in that case.
Okay.
All right, so we have this. Quick calculation over here. Triple integral of 3 minus y dy dx, negative root 3 x squared and 3. Integrate this one, that's not 0, that's negative root 3 to root 3. I have what over here? I have, yes.
Shouldn't that be x squared instead of x cubed?
Thank you. Yes. So it's going to be 3y minus y squared over 2 from x squared to 3. I really have to get this tip fixed, because this is getting really annoying to write with. Negative root 3 to root 3. Plug in 3, so we get 9 minus 9 halves minus 3x squared plus x to the 4th over 2 dx. This together is 9 halves. So integrate, now you have 9 halves x minus 3 and 3 would cancel, so just x cubed, plus x to the 5 over 10. From negative root 3 to positive root 3. And is equal to a number. There we go. Done. A number. Perfect. We were able to accomplish that. Should I do the, we have time for one more. Should I do the sine one on the top or the e to the y one on the bottom? Because we are, that way we're not only doing the planes and things. Sine one? Okay, problem 16. So problem 16, we have the coordinate plane have the line, have it here, and then I have this and that. Oh, it's terrible. And that, good. It's better. Still terrible, but better. Better, terrible. We know that this point here is pi, 0, and that immediately makes this line to be y equals x, which means this plane is y equals x. And then this point over here is 0, pi, 0, which is on the y-axis. And the top over here is z equals sine y. And the bottom of the whole thing is z equals 0. When you shine the light from the top, right, so I can just put the rays like this, meaning shine light from the top, I'm going to get the domain, and this is my y-axis. This is where you have to be very careful. Very careful. Look at what you have. You know you have y equal x. That's a 45-degree line, right? Do I connect this line down to x or across to y? To y. It's very easy to make that mistake. So we cross this to y because this is your line over here, y equal x, right? That's the 45-degree line. And now you see that line is connected to y-axis. It's not connected to x-axis, right? So you have to be very careful with those kind of things as you go. And now we're going to put, again, boring, right, dx. Now from the picture we know this value is pi. We also know this value is pi, so that alleviates calculations, which is great. We have already dx is the boss. The other one over there is dy. So by process of elimination, dz goes on the inner one. And I have to set up my triple integral. dz, dy, dx. We see that 0 to pi for the x, right? Talk to me about y. X to pi, very good. X to pi, because the bottom of the representative rectangle is writing y equals x, and the top is writing y equals pi. So that's good. And what is happening with my z's? Well, 0 to sine y, very good. 0 to sine y because the bottom of the object is flat, it sits on a desk, and then the top is round, right? The top rounded part is one that collects dust, right? So that's the top of the object. And that goes on the top of the integral limit. So now I have my double integral 0x pi pi. Integral of this is just going to be sine y, right? Because you integrate z and then plug in sine y. When I integrate sine y, what do I get? Very good. From 0 to pi, still have dx to deal with. 0 to pi, what do I have here? When I plug in cosine, what's cosine of pi? Excellent. Minus, and then when I plug in 0, nice. This is dx, so the whole thing is 2 pi. So that's problem 16. Good. Next class is cylindrical and travel, but it's a long class, right? 3 hours. The plan is to actually spend some time as like a separate lecture almost. Well, it is a separate lecture, which is not in the book, and that is on just on order of integration, switching the order of integration, double and triple integrals, and picking the right order, right? So we're going to do that as a separate lecture. Again, that's broken over all sections in a book. I'm going to condense that idea into the single extra lecture, so there will be no designation 13 point whatever. And then we'll do the cylindrical and spherical integrals. If we have time, we will deal with the center of mass for mechanical engineering, right? Center of mass, which leaves us with a single 13.7 lecture. We can start chapter 14, right? See you all Friday.